In lesson 7.1, we're going to be graphing exponential functions. And so I'm going to teach this in two different parts. Today we're going to learn about exponential growth, and then the second part of the lesson we will discuss exponential decay. I've listed here the Common Core standards and the mathematical practices for this lesson. Previously, you've graphed polynomial functions, and now you're going to graph exponential growth functions, and then in part 2 you'll be graphing exponential decay functions. New vocabulary for these two lessons is exponential function, exponential growth, asymptote, growth factor, exponential decay, and decay factor. Okay, beginning with exponential growth, there's something you need to know about exponential functions and exponential growth. One type of an exponential function is the exponential growth function. It's the type of function that's in the form f of x is equal b to the x, where b is greater than 1. And the graph of an exponential function has an asymptote, and an asymptote is simply a line that the graph of the function approaches, but never quite touches. So the key concept that you see here is listed on page 451. Notice that the type of graph is continuous, it's one-to-one and increasing. The domain is all the real numbers, and the range is all positive real numbers. The asymptote is the x-axis, and it intercepts at 0, 1. Now we're going to graph y is equal 4 to the x. We'll begin by making a table of values. Notice we've got 2 negative, 0, and 2 positive values, and then we simply connect the points to sketch a smooth curve. So the domain is all real numbers, and the range is all positive real numbers. So which is the graph of y equals 3 to the x? I'll let you take a moment to do your table of values and then come back and find the answer. The answer is C. Another key concept is about transformations of exponential functions. Notice this function is equal to a times b to the x minus h plus k. Now looking at h, this tells us what our horizontal translation would be. If h is positive, it goes h units to the right, and if h is negative, it goes the absolute value units of h to the left. K indicates our vertical translation. It'll go k units up if k is positive, and the absolute value of k units down if k is negative. And then we have the orientation and shape of our graph, and that's denoted by A. If A is less than 0, then the graph is reflected in the x-axis. If the absolute value of A is greater than 1, the graph is stretched vertically, and if it is less than 1, then the graph is compressed vertically. So let's look at some graph transformations. They tell us to graph the function of y is equal 3 to the x minus 2, and they want us to state the domain and range. So first of all, the parent function of this graph would be y is equal to equals 3 to the x. And we just note that it will be translated down 2 units because k is minus 2. We find a table of values so that we can plot our points. And notice the domain is all real numbers, there are no limitations, and the range is y such that y is greater than negative 2. Now let's graph the function y is equal 2 to the x minus 1. This equation represents a translation of the graph. The parent function y is equal 2 to the x, and it's going to go to the right 1 unit. The domain is all real numbers, and the range is y such that y is greater than or equal to 0. So now time to check your progress. Graph the function y is equal 2 to the x minus 4, where k is minus 4. Pause for a moment, do your calculations, and come back and see if your answer is correct. Awesome. The answer is C. Notice that it goes down. It's translated down 4 units. Good job. Graph the function y is equal 4 to the x minus 2, and k is a positive 3. Pause for a moment, do your calculations, and then come back and see how correct you are. All right, notice that this graph is the only one translated 3 units up. Now I would like for you to take just a moment. It's also in your textbook to make it a little easier. We're going to talk about modeling exponential growth when it has a constant % of increase over a specific time period. If you look in your text on page 453, there is a function, a to the t is equal to a times the quantity of 1 plus r to the t. Sorry about that. My cat just walked over my computer. So we can plug these numbers into that function, where a is 1.020 in billions, and r, the rate, we're taking the percentage here, 19.5, and we're changing it to a decimal by moving it 2 places to the left. Then we can simply substitute into the function. So y is equal to 1.020 times 1.195. Remember that our growth factor was 1 plus our rate to the t. Then we'll graph that equation. Notice our time is across our x-axis. So now I would like for you to use that same function to find the answer to this cellular phones problem. Pause for a moment, then we'll come back and check your answer. Good job. You got the answer D? Excellent. So we simply just had to substitute in A, and R is changing our 11% to a decimal. So here's A, and 0.11 is our rate. And decay functions will be something for next time.